everybody. I hope you guys are having a wonderful day today. So our lesson for today is on section 2.1 from the textbook, which is all about sets. So let's start off by talking about what a set is. So a set is basically a collection of well-defined objects. So these objects can be numbers, they can be letters, they can be basically anything. Like you could even have them be people. And sometimes we'll name a set with a certain symbol. So for example, if we have the set of the letters A, B, C, D, E, and F, we could name that set, which we're writing in brackets here. We could name that set the set S. And the way that we describe the things in a set is we use this symbol here. So this symbol means that A is an element of S, or basically that A is an object that is in the set S. And if you cross out that symbol like this, that means that Z is not an element of S, because Z is not in the set. So this symbol means that whatever you're talking about here is in this set here. And you don't necessarily have to name your set. You could also write this as like A is an element of the set A, B, C, D, E, and F, like this. That would also be accurate. But sometimes we will name sets just to make them so that they're like not as long to write, essentially. So there's actually several different ways to write sets. So we can write sets with a description. So I could literally just describe the set I'm talking about, like the set of odd counting numbers. Or you can use the listing method, where you actually list out all of the elements of the set. And if you have an infinite set, like the set of odd counting numbers, you can use like this ellipses to show that the pattern goes on forever. Because obviously it's not possible to list all of the odd counting numbers because there's an infinite number of them. But they do have a pattern that's predictable. And so you can write it out as a list like that. Or the last type is to write it in set builder notation. So with set builder notation, you define what's in the set as like a variable, and then you define what conditions that variable needs to meet. So in this case, if we were writing the set of odd counting numbers, we would say it's the set of all x such that, so this line right here is basically separating the variable from the conditions that the variable needs to meet. So this would be the set of all x's such that x is an odd counting number. And so these are the three different ways that we can use to write sets. And I kind of mentioned this a little bit on the last slide, but we have finite sets and infinite sets. So finite sets are ones that have a specific number of elements that's countable. So like this set here has 4 elements. If we have the set of n such that n is a whole number between 8 and 14, I could rewrite this set in list notation, and I could say, well, the whole numbers between 8 and 14 are 9, 10, 11, 12, and 13. And because there's a specific number of elements in this set, this makes it a finite set. And the number could be huge, like you could have the set of all humans on Earth, but it's still a finite number because it has a specific number of elements in that set. And then we also have infinite sets. So you might have the multiples of 4. Well, there's an infinite number of multiples of 4, and so this would be an infinite set. Or if you had the set of all x such that x is a number between 0 and 2, well, if it's just numbers and not a whole number, well, there's an infinite number of numbers between 0 and 2 because you have 0.1 and 0.00001, and you have like an infinite number of decimals and fractions and irrational numbers between 0 and 2. And so that's what makes that an infinite set. And there's a special type of finite set called the empty set. So the empty set can be written in 2 different ways. One way is you can write the set brackets with nothing in between it because it's the empty set, but it's more common to actually use this symbol, which is the symbol or the name for the empty set. And this is a finite set because the number of items in the empty set is 0. And so this is a special type of finite set that shows up basically whenever a set doesn't have anything in it. So let's talk about what makes two sets equal. So we say that two sets A and B, which I've named these sets A and B, but they could be any sets. These two sets are going to be equal, which we write as A equals B, if and only if they have precisely the same elements. So if we look at these different sets I've defined here, in this case, A and B are equal to each other, so we could say A equals B. And the reason that we know they're equal to each other is because they have the exact same elements. A has a hashtag sign, and B has a hashtag sign. A has an asterisk, and so does B. A has a $sign, and so does B. And A has an @ symbol, and so does B. And so we say that A equals B. And we can also say that A equals C, because if we look at A and we say, okay, well, A has a hashtag sign, well, so does C, and C happens to have it listed twice, but it's still the same element. So they do have precisely the same element. And A has a asterisk, and so does C, and it has 4 asterisks, but it's still the same element. And so, we could keep on going and say, well, they both have $signs and they both have an @ symbol. And so that makes A equals C. And so usually we actually won't write a set like this because this is just a more complicated way of writing the set. But we could also say that C equals the set containing a $sign, a hashtag, an @ symbol, and an asterisk. And this would be a more simplified way to write the set C. However, we would say that A does not equal D because D is missing the hashtag sign and the hashtag sign and the asterisk symbols. And so the set A does not equal the set D because some of the elements are missing in set D. Another relationship that we can describe between sets is the idea of a subset. So we say that A is a subset of B if and only if every element of A is also an element of B. So if we look at these two sets, because little a is in A and it's also in B, and little b is in A and also in B, and little c is in B, and little d is in B, and little e is in B, because every single element in A is also an element of B, then we can say that A is a subset of B. And so that's the idea of a subset. And then we can be more specific with this, and we can define a proper subset. So if A is a subset of B, like we defined on the last slide, and B has an element that is not in A, then A is a proper subset of B. So in this case, A, we could say, is more precisely a proper subset of B because B has at least one element. It actually has a whole bunch of them, but it has at least one element that is not in A. So when we're talking about subsets, it's possible that the two sets could be equal to each other. Because if you had two sets that were equal to each other, they would be subsets of each other because every element in one of them would also be an element in the other one and vice versa. And so the idea of a proper subset is more precise where basically it's saying that they can't be equal to each other in order to be a proper subset. So most of the time when you're talking about subsets, they will also be proper subsets. But if the two sets are equal to each other, then they'll be subsets of each other. So one of the things that we often use to help us understand sets and to kind of visualize what it means is the idea of a Venn diagram. So if we were drawing a Venn diagram of a subset, you would basically have your bigger set, which I've decided to be B, and then A would be inside of B. and all of the different elements in A, whatever they are, whether they're letters or numbers or people or objects or whatever they are, all of those objects that are in A will also have to be in B, and it's possible that B could have other elements that are not in A. However, they don't have to be. You could have the two sets being equal, and this space in B that's not in A could just be empty. But with a proper subset, the definition of it says that B has to have at least one element that's not in A. So if you have this proper subset symbol, that means that we have at least one element that's in the region that's in B, but not in A. And so this would be a Venn diagram depiction of what subsets are versus proper subsets. Another relationship that we talk about between sets is the idea of equivalent sets. So equivalent sets are different than equal sets. And we write them with this little squiggly symbol. And basically, two sets are going to be equivalent if there's a one-to-one correspondence between them. So what it means to have a one-to-one correspondence is that the elements of the set can be matched up so that each element is matched to exactly one element in the other set. So for example, a one-to-one correspondence could be, well, I'm going to match X up with A and Y up with B and Z up with C. That would be a one-to-one correspondence because each element in A is getting matched to exactly one element in B. And there's actually a lot of different one-to-one correspondences. Like you could also say I'm going to match X up to B and Y up to A and Z up to C. That would also be a one-to-one correspondence. So you actually don't even have to define what the one-to-one correspondence is to determine if they're equivalent. You just have to know that there is a one-to-one correspondence between them. So why don't you guys try this example? So pause the video and I want you to identify whether each of these pairs of sets are equivalent, equal, or neither. So pause this video, try it out, and then restart it to see what the correct answer is. Okay, so let's start by looking at sets A and B. So on sets A and B, I'm looking for a one-to-one correspondence between these two sets. So I could say, well, I'm going to have 1 in A match up with 2 in B. 2 in A is going to match up with 8 in B. 3 will go to 0. 4 will go to 3. 5 will go to 9. And because each element in A gets matched up with exactly one element in B and vice versa, this shows us that they are equivalent, but they are not equal to each other because they don't share the exact same elements. Like B has a 0, but A does not, or A has a 5 and B does not. So they're equivalent to each other, but not equal. If I wanted to compare C to A, again, I'm just looking for a one-to-one correspondence to determine whether or not they're equivalent. So I could say, well, I'm going to match 1 to 5, 2 to 2, 3 to 3, 4 to 1, 5 to 4. So that tells me they are equivalent, but they're also equal to each other because they both have a 1, they both have a 2, they both have a 3, they both have a 4, they both have a 5, and so this means that they're equal to each other. So all equal sets will be equivalent to each other, but you may have some sets that are not equal, but they are equivalent, like A and B were. On D and A, these two sets are equivalent but not equal because you could create a one-to-one correspondence between the sets or the elements of A and the elements of D. And then for set E, E is actually going to be equal to set C because if we look at set C has a 5 and so does E. Set C has a 2 and so does E. It's listed twice, but it's still the same element, so it has the same element there. Set C has a 3 and so does E. Again, it's listed twice, but that's fine. C has a 1, so does E. C has a 4, so does E. And this 5 I should have actually circled earlier because C has a 5 in it. And so because C and E have precisely the same elements, that makes them equal. And then for sets F and D, these ones would not be equal because D has an V in it, but F does not. And so these would not be equal. And they're also not equivalent because if I were to say, okay, I'm going to have V match up with Z, so it goes with all of the Z's, and then let's say I match up W with Y, I think that's the only Y in there. And then let's say I match up X with X, so X would match up with both of the X's. And then let's say I match up Y with W. Well, Z does not have anything to match it up with. And so that means there's not a one-to-one correspondence between D and F, and so they're not equivalent either. They're not equal and they're not equivalent. And with E and F, if we try to make a one-to-one correspondence with that one, I'm sorry it's getting kind of messy, but I could say, okay, I'm going to match up 1 with Z, so I'll match up 1 with all the Z's, and let's say I match up 3 with Y, so this 3 is also going to match up with Y, and 4 gets matched up with X, and let's say I put 5 with W, and so this 5 would also go to all those W's. That's like super messy. But basically on this one, 2 doesn't get matched up with anything. And so that means that E and F are not, well, they're obviously not equal because they don't even have any of the same elements, but they're also not equivalent. And so this would be the correct answer for these. So when we're talking about sets, we have relationships between sets. So that's what we've been talking about so far. Like you can have 2 sets that are equal, 2 sets that are equivalent. You can have sets that are subsets or proper subsets of each other. Or you can also talk about the relationship between the sets and the things in the sets. So if X is an object in set A, you can say that X is an element of A. But we also have what are called operations on sets. So the idea of an operation is you're going to do something to 2 sets and make a new set essentially. Or sometimes, like with the complement, it may only be 1 set. But most of the time we have what are called binary operations. So a binary operation means you have 2 sets and you do something to those sets to make a new set. So let's talk about the first type of operation, which is called a union. So the union of A and B, which we write like this, is a new set. So this right here is going to be the name of the new set that we're creating. And this set is going to consist of all of the elements that are in set A or in set B. So if we have set A equals the set containing A, B, C, D, E, and set B contains D, E, F, G, well, the set A union B, it's basically going to have an A, a B, a C, a D, and an E in it because it has to contain all of the elements from set A. And then it's going to have a D, an E, an F, and a G in it. And so this set is called A union B. And if we were to draw this in a Venn diagram form, basically the set A union B would be the set that contains all of this, all of the elements in this section, as well as all of the elements in this section. So this right here would be A union B. And then an intersection is a different binary operation. So the intersection of A and B, which we write like this, is the set of all elements that are in both A and B. So if we take these same 2 sets that we had on the last slide, the intersection of A and B is going to be the new set that contains D and E because both of these sets contain a D and both of them contain an E. And so that would be the intersection of A and B. And the symbols for union and intersection are very similar. So the union symbol looks like this, and the intersection symbol looks like this. So the way that I like to remember which one is which is that the union looks like a U, so it's like, kind of like the name of it. And then for the intersection, I kind of look at it that it looks kind of like an A, and it's the set of all elements that are in both A and B. So I don't know if that's helpful for you guys to think of it that way, But that's the way that I remember that this symbol is the set of all elements that are in both A and B. So if we were going to make a Venn diagram of this, the part of the Venn diagram that contains all the elements that are in both A and B would be this region right here. And so this section of the Venn diagram here would be the set A intersect B. So the next operation that we're going to learn about is the complement. And this one is just an operation that involves a single set. So our last two involved two sets, so they were a binary operation because you took two sets to make a new set. But in this one, we're only going to be working with one set. So the complement of a set A, which we write with an A with a little line over it, is the set of all elements in the universe that are not in A. So the universe is defined by whatever it is you're talking about. So like in this example where I have set A equals the set A, B, C, D, E, well, my universe could be all of the lowercase letters. And so basically the universe is all of the possible elements that are relevant to what you're talking about. So in that case, if A is the set A, B, C, D, E, and the universe is all of the lowercase letters in the alphabet, then A complement is going to be F, G, H, I, J, K, L, M, N, P, all the way down to Z. Because these are basically all of the things in the universe that are not in A. And so when you're drawing a Venn diagram of this, the universe is usually represented with a box because it's going to represent everything that's possible. And A complement is going to be all of the space outside of A, because the complement of A is all of the elements that are not in A that are in the universe. And so that's how you would draw a Venn diagram for the complement. The next operation we're going to look at is the difference of sets. So if I have the difference of sets A and B, this is going to be the set of all elements that are in A that are not in B. So if I take these two sets that we've been working with for the last few examples, A without B, or the difference of A and B, is going to be the set A, B, and C, because these are the elements that are in A but not in B. So you could check this one by one and you could say, okay, the letter A, that's only in set A and it's not in B. And so that means it goes into the difference of A and B. Same thing with B and C. Those two letters are in A but not in B. However, D and E do not go into the difference of sets because D and E are also in B. And the difference of the sets is going to be the set of all the elements that are in A that are not in B. So if we were to draw this on a Venn diagram, the difference of sets A and B would basically be this region right here. And it does matter which order you write this in, because if I were to write the difference of sets B and A, that would be this region here. And so the order does matter, like which one you're writing first and which one you're writing second, because the difference is defined to be the set of all of the elements that are in the first set that are not in the ones in the second set. And then the last type of operation we're going to look at today is the Cartesian product. So the Cartesian product of sets A and B, which we write as A cross B, is going to be the set of all the ordered pairs such that the first element of the ordered pair, or the first part of the ordered pair, is an element of the first set. So since we're doing A cross B, that means that we would have any element that's in the set A. That's going to be the first part of the ordered pair, and then the second part will be an element of the second set. So let's say, for example, that set A is the set that contains the elements A, B, and C. The set B is the set that contains the elements 1 and 2. Well, in that case, the set A cross B is going to have 6 elements. You're going to have the ordered pair where you have A and 1, the ordered pair A and 2. Then you're going to have the ordered pair B and 1 and B and 2, and C and 1 and C and 2. And so basically, in this case, our new elements are ordered pairs. because these are still objects, even though they're kind of like a combination of the objects in our original set. These are the individual objects. And we'll talk about this later, but this is very related to the operation of multiplication that we learn about in elementary school. So we'll talk more about that later, though. And when you're making the Cartesian product, one way that you can make sure that you get all of the ordered pairs, because you do have to make sure you get every single possible ordered pair, is you can set up a table where you list the different elements in the first set and the elements in the second set, and then you make ordered pairs in the table from there. So that can be a helpful strategy to make sure that you get all of the ordered pairs in the Cartesian product. But you can also just list it as long as you don't miss any. So that's how the Cartesian product works. And on your homework, you'll see some problems where you have multiple operations. So a binary operation involves two sets, but you can do combinations of these binary operations. And the way that you know which ones to do first is determined by where the parentheses are at. So for example, if I was trying to find the universe without the union of A and B, the way that I would look at this is I would first of all look at my set of parentheses and I'd say, okay, well, what does that give me? Well, A union B in a Venn diagram is this region right here. And so that would be A union B. And then if I want to do the universe without that, then basically I'm going to take the universe and take away the A union B part. And so this part of the Venn diagram would be the expression for this compound operation. So if I was asked to draw a picture or a Venn diagram of that, my Venn diagram would look like this. Because the A union B was the stuff I had shaded in blue, and if you do the universe without that, that would be this region here. And the placement of the parentheses does make a difference, because if I was to do the universe without A first, well, the universe without A is basically this whole region right here. So that would be that part, and if I union that with B, then that's going to be this region that includes all of the blue stuff, as well as all of the stuff in B, which includes this little part as well. And so this is a different Venn diagram than the one that I have on the left. And so this kind of illustrates how the order does matter. Also, it's kind of interesting to note that you could rewrite this as a complement, because the complement is basically the universe without what you're talking about. So this would be equal to the set A union B complement. Those two expressions would end up being the exact same, because the complement of A union B is the exact same space on the Venn diagram. And this part would be equal to A complement union B. And that's what that would look like. And then for our last definition, we're going to actually use some of the terms that we've learned earlier in this lesson. So the definition of a disjoint set or two disjoint sets is that if their intersection equals the empty set. So basically what this means is, remember, the intersection is the set of all elements that are in both A and B. And so if the intersection is the empty set, that basically means that A and B do not share any elements. And if we were to draw a Venn diagram of that, that basically means that this region in the overlap of A and B is empty. So there is no overlap, which means you could actually draw the Venn diagram like this, where sets A and B are totally separate from each other because there is no overlap between them. And so if two sets meet that requirement, then we say that those two sets are disjoint. So to summarize our lesson, we've learned lots of different definitions about what sets are and how we can write them, and the relationships and operations that we can define between sets. So if you have any questions, let me know, and I hope that you guys have a great day.